So we are going online now.
Okay, very good.
Hello, everybody. It's a pleasure to be here. We are on our distinguished lecture talk, and today we have an EDS distinguished lecture from Professor Dr. Edmundo Gutiérrez. Just let me say a few words. He got his PhD from Catholic University of Leuven, Belgium, in 1993. He was appointed as head of the Inaue Department of Electronics in 1999 to 2000. He spent some time as a design manager of the Motorola Mexico Center for Semiconductor Technology in Puebla City, and after as a research manager of the Mexico Intel System Research Center in Guadalajara City. Professor Gutiérrez is author of the book Low Temperature Electronics, Physics, Device, Circuits, and Applications, and the book Nanoscaled Semiconductor Devices, Physics, Modeling, Characterization, and Social Impact, Societal Impact. Currently, he's the General Director of Inaue in Puebla, Mexico. He's also a member of the Mexico National System of Researchers, editor of the Transactions on Electronic Devices, and editor-in-chief of Transactions on Devices and Materials Reliability. It's really a pleasure to have you here. The floor is yours.
Okay, thank you very much for the introduction. Okay, okay, have a good day. I hope you have a good day there in Brazil. So today I will talk about the cryogenic performance of CMOS technologies as a possible application for quantum computing. So we have been working on the low temperature electronics since more than 25 years ago in Mexico, and we have 2 different labs where we are capable of going down to 4.2 Kelvin. And in one of those labs, we also have the facility to go down to 300 millikelvin, which is a temperature quite good for implementing applications for quantum computing. I will talk about that during this presentation. So what is the motivation of working on low temperature electronics, which we call sometimes cryoelectronics? It's because there is a big trend in these days of using quantum computing. So quantum computing is a good option for accelerating the computer applications, and but there is one condition for having quantum computing. So there is a need to operate the electronic systems at very low temperatures, and for instance, for the sub-Kelvin, dilution refrigeration is needed in order to operate the temperature down below 1 Kelvin. And there is also one issue with these dilution refrigerators. One is that they cannot handle very high power capability. For instance, that power capability or joule power is in the range of 20 to 50 microwatts. And if we think in putting the electronics together to the quantum computing devices, so that means that we should use a CMOS technology. If we have a 1 volt CMOS technology, the current cannot be larger than 20 to 50 microamps. So that is the safe operating window for CMOS devices if we want to put the electronics together to the quantum computing devices. So then, what are the chances for cryo CMOS? Then we have 3 options. The first option is what we call the Josephson qubits, which operate in the range of 10 to 40 millikelvin. Then we have another option, which are called the spin qubits. The spin qubits are able to operate in the range of 1 Kelvin, but they require the use of magnetic field. And then we have other options, which is called the charge qubits, which are based on the use of voltage pulses in order to inject charge. And that qubit technology is capable to operate in the range of 4 Kelvin. So this evolution, this positive evolution in the temperature operation of these qubits devices is giving a hope for the use of using cryo CMOS together with the qubits. So now that in these days, what is happening is that we have the qubits placed in a very cold environment, and then we have an interface that connects to the readout electronics, which is regularly operated at 4 Kelvin. So in these days, there is a motivation for putting everything together, not only the qubits operating in the cryogenic environment, but also the electronics in the same chip. That's why people is getting interested in characterizing and modeling CMOS technologies for very low temperatures. Okay, so this is the full temperature range that we can have from, let's say, below 4.2 Kelvin up to 300 Kelvin or even below. But let's see what are the characteristics of these different regions. So as you can see, so we have the temperature range in which we are interested is the sub-Kelvin quantum operation. That is the temperature regime where we can find or we can observe many quantum effects. Then we have a little bit above 4.2 Kelvin, we have the strong freeze-out effect. Then we have the 50 Kelvin, which is a boundary condition where we have an interaction between the electrical and the thermal properties of devices. So below 50 Kelvin, as we will show during the presentation, there is a strong correlation between the thermal and the electrical performance of devices. So we cannot isolate both effects. So we need to work and understand how the electron devices are operating in terms of the electron transport and phonon transport, which is the thermal, which is ruling the thermal properties of these devices. So these two figures show something which is quite interesting. The figure above is the energy gap as a function of temperature. As you may see, there is a range where the energy gap increases more or less linearly from room temperature down to about, let's say, 125 Kelvin. Then we have a sort of a saturation regime, which is from, let's say, 4.2 Kelvin up to 50 Kelvin. That's the range where the most of the electrical properties and of the transistor comes to a saturation. Below, there is carrier mobility. Carrier mobility is interesting because it's a pretty complex parameter. So his dependence on temperature is also a function of the doping level and the number of electrons, free electrons. So depending on the doping conditions and the number of free electrons, the performance of the carrier mobility as a function of temperature changes. In this case, we are looking at the carrier mobility due to phonons. As you may see, is always increasing as we reduce the temperature, because as we reduce the temperature, the number of phonons reduces, and then the screening factor also reduces. Then we have surface roughness, which is pretty flat at very low temperatures. And then we have the effective mobility in blue color. As you may see, it reaches a maximum value at about 150 Kelvin and then goes down to very low values at very low temperatures. But that behavior depends on the doping condition. Okay, let's move ahead. So these two graphs are the experimental results of 22 nanometer FinFet. As you may see, the transconductance in this case, in this particular technology, is always increasing when we move from room temperature down to 4.2 Kelvin in this case. And that's the case when we operate the transistor at a drain voltage of 0.1 volt. However, if we increase the drain voltage to 0.4 volts, as you may see on the figure right below, so the transconductance reaches a maximum at about 200 Kelvin and then goes down, and it reaches a minimum value at about 30 Kelvin degrees, and then there is a sudden increase below 30 Kelvin. I will talk a little bit more about this in the next slides, because this is a pretty interesting effect, which is correlated to the electrothermal boundary that I already talked about a few seconds before. So the thermal properties at cryogenic temperatures are very important. At the left side, you see the thermal conductance as a function of temperature. As you may see, the thermal conductance of the thermal resistance, in green color as a function of temperature reduces as we reduce the temperature from room temperature down to about 70 Kelvin, and then goes up to very large values for temperatures below, let's say, 50 Kelvin. And that's quite important, because if you are operating a device at temperatures below 50 Kelvin, then any heat that is generated by the transistor will increase the temperature, the local temperature of the transistor, and then there will be an electrothermal interaction, which is quite strong at very low temperatures. The heat capacity is shown at the right plot, and that is also very important. As you may see, as the temperature reduces, the heat capacity reduces. That means that at very low temperature, there might be a temperature and a bias condition where the thermal resistance equals the electrical, the thermal transient time is equal to the electrical transient time. So there might be a mix of electrical and thermal responses at very low temperature. So it's quite difficult to see which of those is dominating the electrothermal performance of devices at very low temperature, because of the time constant. The thermal time constant might be equal to the electrical time constant in some cases. Okay, CMOS works very well at cryogenic ambient temperatures, as you may see in these two plots. This is a 22 nanometer P-type FinFet technology. It's a 120 nanometer in a wide transistor and a 20 nanometer channel length transistor. As you may see, the ID versus BD characteristics and ID versus BG characteristics work very well. So in the case of the ID versus drain voltage characteristics, you may see that the joule power goes from 54 microwatts to 700 microwatts. So that is already exceeding the joule power required by qubits. So this is already one issue. So the only chance for these CMOS devices is to operate them in a very low bias condition, so in order that we can reduce the power dissipated by the devices. So what is the issue? So this is a regular MOS transistor. So if we are having self-heating effects, what we are having here is that we have a hot spot, which is very close to the drain, and then the heat is trying to move away from the active region of the transistor. So there are 4 thermal paths. One is down through the bulk, and then we have 2 lateral branches. One is flowing through the source, the other one is flowing through the drain, and then we have one path upward through the gate oxide. So, and this is important because the thermal resistance of the oxide is much larger than that of the silicon. So the heat prefers to flow away through the drain and the source instead through the oxide. So that can be a big issue, for instance, for SOI devices where they are thermally isolated because of the buried oxide. So this is something that we have to keep in mind. And look at this. These are the specific thermal resistance for the different materials that we are using in this technology. So we have here the thermal resistance of silicon, which is the in magnitude is the smaller magnitude. Then we have the polysilicon, which has a little bit larger thermal resistance. Then we have the silicon dioxide, and then the varnish. The varnish is the glue that is used to attach the silicon die to the sample holder in the cryostat. And as you may see, the varnish is the material with the larger thermal resistance. So in this case, what we see is that the heat should prefer to flow through the source and the drain, and then perhaps through the gate oxide, but it depends on the thickness of the gate oxide. If the gate oxide is very thin, then the heat is able to flow through the gate oxide. We will see some experimental results in the next slides. So I'm just checking my time. So one issue here is that the thermal components are technology, geometry, and structure dependent. So depending on the transistor structure, the thermal components might change, and also depends on technology, because the thermal properties depends on doping and also on geometry. Okay, so we have two different experimental setups. This is the setup that we are using in collaboration with the Germany group in Jülich. It's a 6.5 closed cycle dilution refrigerator. You may see there the two silicon dies, which are glued or attached to the sample holder, and then you may see the needles that are making the electrical contact to the devices. So this is one of the experimental setups that we use, and for the characterization of devices. Then we have the Mexico 250 millikelvin closed cycle dilution refrigerator. This is a big instrument, and then there you may see the sample holder and some of the different temperature stages. So we have liquid. We have 3 helium liquid ultra cold stage, and then we have the reservoirs for the liquid helium 3, and then we have on the top at the right picture, at the right side of the picture, at the right side on the top, we have the socket with the sample holder that we put the packaged devices in there. So this is the general configuration of the experimental setup that we have in Mexico. And this is the characterization of the cryogenic system. So it's an experiment that takes a long time, as you may see by the red plot. So for the system to go down to 300 millikelvin, it takes about 1 hour. Then it gets stable, as you may see there, and you may see there probably 2 small peaks, and those 2 small peaks are enlarged at the upper side of the plot. You may see that there are 2 large peaks. Those peaks belongs to the point the point where we are characterizing the transistor, the IDBD characteristics. You may see that the temperature of the cryostat is going up from 350 millikelvin up to 390 millikelvin, and then when we stop the measurements, the system goes down with a thermal time constant. Then we proceed to the next point, which is the ID versus BG characterization, and you may see how there is a self-heating effect happening at very low temperatures. In this case, we use a maximum power of 889 microwatts. So this is very important because in order to perform this characterization and these experiments at very low temperature, we need to have a cryostat which is able to handle a very high thermal load. And these are the some of the experiments that we perform on a 14 nanometer p-type FinFet. And there are 3 plots there. There is one in black, which is the measurement performed at room temperature. Then we have the one in blue color is at 4 Kelvin. And then we have the one in red color, which is the 350 millikelvin. So the system is working pretty well. So we are pretty sure that the system is ready for characterizing these technologies. And that is what we are going to, what I'm going to show in the next slides. This is the thermal time decay for each of the bias point. As you may see, so we bias the transistor, and then it takes about 2 or 3 minutes for the system to stabilize. So, and then you can imagine how long how long in time is a characterization if we are taking all the points for the IDVD and IDVG characterization. So these are experiments that takes hours and hours to complete. So, well, this is just a drawing of how the transistor, the package transistor, is inserted in the socket, which is pretty close to the sample holder. And there are some simulations in order to understand how the heat is diffusing away from the sample holder. Okay, so this is the test structure that we use for extracting the self-heating effect in a 65 nanometer technology. It's a polygate technology with a gate oxide thickness of 1.9 nanometer, and the transistor has a width of 12 micrometers and a length of 60 nanometer. As you may see, the gate is a sort of a 4-point calibration system. So we bias the gate by putting the voltage at the electrode G1, and then we flow a small current through G1, and then we measure the voltage drop through G2 and G3. So by measuring that voltage drop, we are just characterizing the electrical resistance of this poly. So the resistance of the poly is calibrated from room temperature down to very low temperatures. And then by calibrating this thermometer, we are able to measure the heat that is generated by the transistor. Of course, the transistor the heat is generated at the active channel of the transistor, pretty close to the drain. And then the heat is flowing through the oxide, and then is measured as a temperature at the gate. So in that way, there is a difference between the heat that is generated at the active channel and the one that is measured at the gate. So, but let's have a look at the experimental results. So this is the calibration plot. So we measure the gate resistance as a function of temperature in the black dots, and then we extract the error. The error is pretty low. The error is in the range of 0.3%. And that is a calibration curve that we use for using the polygate as a thermometer. Okay, and here you see the ID versus BD and ID versus BG characteristics of these transistors, the 65 nanometer NMOS transistor at 6.5 Kelvin. So we use in this case the setup that is in Germany, and which is able only to go down to 6.5 Kelvin. So the technology is operating very well. So there is no big issue with this technology for being operated at cryogenic temperatures, as you may see from these two plots. But okay, this is the once again the drain current as a function of the gate voltage with the drain voltage as a parameter. And but look at this. This is the incremental temperature. So this is the temperature that we are measuring at the gate. Is the temperature difference between the gate and the sample holder. So as you may see, the temperature might go up to 94 Celsius degrees. So the device is heating quite a lot. So the internal temperature is pretty high. So this is very important, because then what we are seeing here is that the device is not really operating at 6.5 Kelvin, but it's operating at almost very close to 100 Celsius. So that means that we cannot use this technology in close proximity to qubits, because of the heat is diffusing away and then it's changing the temperature of the qubits. Okay. And this is the ID versus BD characteristics. Okay, let's have a look at the incremental temperature. There you may see the incremental temperature is also in the same range, pretty close to 100 Celsius degrees. So this is as I already mentioned, this is a 65 nanometer bulk CMOS technology. And well, as you may see, there is a very large fraction of self-heating in these devices. But okay, I will move to the next slide. So what we measure here is the incremental temperature as a function of the joule power. As you may see, this is not a linear relationship, and one should know that there is a linear relationship between the thermal, between the temperature and the power through the thermal resistance. So this plot is telling us that the thermal resistance is changing because the local temperature is changing. So we have only a very small fraction where there is a linear relationship between the incremental temperature and the joule power through the thermal resistance. Okay. So the incremental temperature should be, as I already mentioned, proportional to the power, the joule power through the thermal resistance. So the question is why there is a detour from the linear behavior at very low joule power ranges? Well, that's because when we move to a larger temperature, in this case, the first case is the incremental temperature measured as a function of the joule power at an operating temperature of 6.5 Kelvin. Then we move to the operating temperature of 75 Kelvin. In that temperature range, the relationship between the temperature and the power is linear. So what is this plot telling us? Well, what this plot at the right side is telling us that the thermal resistance is staying constant. So there is no change in the thermal resistance. So only at very low temperatures, as we may see from the left plot, the thermal resistance is changing quite a lot. And that is also a big issue, because we need to have electro-thermal models in order to understand how the current and the temperature, the local temperature, is changing as a function of joule power. Okay, this is what I was telling you. If we are operating the device pretty close to the 70, let's say 80 Kelvin, 75 Kelvin, the thermal resistance is, I would say, pretty constant. Then we should expect a straight line. A correlation between the temperature and the joule power should be a straight line. But if we move to lower temperatures below 50 Kelvin, then the thermal resistance is changing quite a lot, from a very large values to very low, to these very low values. And that is the reason why we are having this nonlinear behavior at very low temperatures. Okay, that's what I was telling you. So this nonlinear behavior that we see on the right side, the upper plot, belongs to this region 8, where the thermal resistance is reducing the magnitude is going down because of the self-heating effect. Then if we look at the other right side plot, the one below, and then it's almost a straight line, because we are located in the constant region of the thermal resistance. So this plot is pretty important because that is telling us that any small change in the local temperature because of the self-heating will change the local temperature, and then it will affect the electrical performance of this CMOS technology, which is being operated at very low temperatures. Okay, together with the Jülich Center in Germany, we developed an electro-thermal model in order to reproduce the incremental temperature as a function of the Joule heating power at different temperatures. In this case, the temperature range goes from 6.5 Kelvin up to 80 Kelvin. As you may see, the correlation between the measurements and the calculation is pretty good. So at this point in time, we are working together with the Jülich Center in Germany in order to develop a sort of a SPICE model in order to integrate the electrothermal interaction in the SPICE model, so the designers can have a better understanding on how the circuits are operating at very low temperatures. Okay, then we move to a 22 nanometer SOI fully depleted technology. So we designed a self-heating test structure, the same as in the 65 nanometer technology. In this case, we use 22 nanometer SOI fully depleted transistor with a width of 10 microns and a length of 20 nanometer. And this is the description of the device structure. So what we have there is the generation of heat and impact ionization. So we perform some measurements on this technology as well. And these are the ID versus VG characteristics with the drain voltage as a parameter at a temperature of 7 Kelvin. And then you may see a sort of a belly here. That belly is basically because of the impact ionization. So we are having impact ionization, so the bulk potential is changing, and then the drain current is moving because of that, the floating potential in the bulk. But we also have heating, which is generated in this technology. I will show that in the next slide. So we also measure the backgate current. As you may see, well, at 7 Kelvin, there is an expected behavior for the backgate current. And this is the substrate current measured from as a function of the gate voltage, with the drain voltage sweeping from 0.1 volt up to 1 volt, except for the substrate current as a function of the gate voltage. For the drain voltage of 1 volt, we see there a small hump in the red color. So that is probably the drain voltage at which the impact ionization is starting to show up in this technology. And this is the case. So we increase the drain voltage up to 1.5 volt, and this is what we see here. There is this belly here, and then we measure the backgate current and also the substrate current, which is an indication of impact ionization. So this technology, which is a SOI fully depleted, is showing this impact ionization, which is already making the analysis of this technology a little bit more complex, because we have also self-heating in this technology, as I will show in the next slide. This is the measured temperature at the gate. This is really amazing. As you may see, for the drain voltage of 1 volt and gate voltage of 1 volt, with this, the measured temperature of the gate goes up to 276 Kelvin. So this is really a hot plate. So this technology is really heating a lot, as you may see from this plot. So of course, the size of the transistor is pretty large, as I already show here. I'm moving back. So it's a transistor with a width of 10 microns and a length of 20 nanometer, and the amount of current that is driving this transistor is 10 milliamps. It's pretty large. Okay. And then the result of that is that we are having a pretty large self-heating effect in this transistor, which is also coupled to the impact ionization phenomena that we are seeing at very low temperatures. So the threshold voltage for this technology and the transconductance as a function of temperature, you may see it here. So the threshold voltage in the black dots is from 150 Kelvin is going up, is increasing as we reduce the temperature. Then it reaches a maximum value at around 40 Kelvin and then goes down. But the transconductance is showing a similar behavior, is always increasing and below the temperature at which the threshold voltage reduces drastically, the transconductance increases drastically. This is a little bit confusing because because of the self-heating effect that is showing up at temperatures below 50 Kelvin, one expects the threshold voltage to go down because the local temperature is increasing, then the threshold voltage should reduce. But we also should expect the same for the transconductance because the transconductance has a positive temperature coefficient. That means that if we reduce the temperature, the transconductance increases because of the mobility increases. But in this case, the mobility is going up very drastically. We don't know yet what is going on in this because we are still analyzing the data. And this is the drain current. This is the drain current for two different bias conditions. In the black dots, we have a drain voltage of 1.1 volt and a gate voltage of 0.65. That is the bias condition at which we extract the threshold voltage. And you may see that the drain current is reducing from 150 Kelvin down to about 100 Kelvin. There is sort of bump, and then the drain current is going up for very low temperatures. The blue color plot is the drain current at drain voltage of 1.5 volts and gate voltage of 0.9 volts. That's the point where we have the highest impact ionization mechanism. And as you may see, the drain current is also increasing as we reduce the temperature. But we don't have any explanation so far for this pretty large increase of the drain current for temperatures below 10 Kelvin, which we believe is pretty coupled to impact ionization and self-heating. We don't know, because we should expect if there is a very large self-heating, which is taking the local temperature up to more than 200 Kelvin, then the current should decrease. But instead of that, it's increasing. So there is something that we are not understanding yet in the performance of this 22 nanometer SOI fully depleted. And we have also data from other technologies that are not showing today, because I'm not allowed to show that experimental data, but is having the same behavior. So there is something that we need to work a little bit more in order to understand why self-heating at very low temperature is not reducing the magnitude of the drain current. This is the gate current as a function of temperature. So we know that the gate current has a positive temperature coefficient. So if we increase the temperature, the gate current increases. So the other case is when we reduce the temperature, the magnitude of the gate current reduces. As you may see that from 150 Kelvin, there is a reduction of the gate current, then we reach a minimum value and then goes up. For temperatures below 50 Kelvin, the gate current increases quite a lot. So that is in agreement with the self-heating effect, because if the local temperature is increasing, one should expect an increase of the gate current, and that is what is happening here. So this is quite in good agreement with the self-heating effect, which is becoming severe for temperatures below 50 Kelvin. But this is what is happening with the gate current. And this is what happens with the maximum value of the back gate current and the substrate current. So the back gate is in the black dots. As you may see, it has a very not regular performance. It has a maximum value, then goes down and then up again. The same happens for the substrate current. And as we know, the impact ionization increases as we reduce the temperature. But in this case, if we are having a pretty large increase of the local temperature because of the self-heating, I should expect a reduction of the impact ionization, but that is not happening here. So we have an increase, a pretty large increase of the impact ionization. So we don't know yet, but something is going, I don't know what is going on with this technology, but we need an explanation for this. So that's a question. What is going on with this technology? Because we have heat generated in the active region of the transistor, which is flowing through the source and drain, and is obviously that is also flowing through the gate oxide because we are measuring an increase of the local temperature in the gate. But there is also an impact in the box and the back gate and substrate of this technology. So we have the electro-thermal interaction. We have the heat, we have impact ionization. Those two phenomena coupled together are giving this strange behavior at very low temperatures. And that is happening here in this region between 90 Kelvin and 30 Kelvin. As you may see here, there are these two bumps in the back gate and substrate current, which are correlated somehow with the appearance of impact ionization. But then we have a minimum value around 40 Kelvin, and then these currents are going up, which are obviously correlated to the self-heating effect, which is pretty severe at very low temperatures. Well, it looks like everything is correlated to the performance of the thermal resistance as a function of temperature. But in this case, this is the thermal resistance that we extracted from a 65 nanometer technology. We should extract also the thermal resistance for this 22 nanometer SOI fully depleted technology because it has different materials to that of the 65 nanometer. But that is something that is going to take a long time because it's not easy, as I already mentioned. These experiments are taking hours and hours to complete. And in some cases, when we are just running the experiment from room temperature down to, let's say, 1 Kelvin, in some cases, the device is not working anymore. And then we need to go back. We need to open the cryostat and repeat all the process that takes days and days to complete. Well, something else. This plot is it's giving information. What I'm plotting here is the incremental temperature in blue color as a function of joule power. You may see that the incremental temperature is increasing as a function of joule power, then reaches a maximum value and then goes down. But it goes down because the gate leakage current increases quite a lot here, and that is influencing the thermometer calibration. That's something that our collaborators from Germany has to adapt in order to take into account for the gate leakage current, because it's also affecting the value of the temperature that we are measuring at the poly gate. This is a correction that they need to make in order to avoid this, because if you look at this sort of behavior of incremental temperature as a function of joule power, this reduction means that we have a negative thermal resistance, and that is not that is not possible. So we need to take into account for the gate current leakage, which is amazing because this is a technology which is operated at very low temperatures, and the leakage current is already present there, even that we are working at very low temperatures. And as we know, the gate leakage current reduces as we reduce the temperature, but then we have also the self-heating effect working together here. So what are the preliminary conclusions? So it's pretty hard to mention or to draw some conclusions at this stage, but what I can say is that we need to solve we need to make use of very complex models that incorporate not only the solution of the classical equations or the Maxwell-Boltzmann equation, but we need also to take into account the electro-thermal performance into the system of equations that need to be solved. So in order to understand what is going on in this technology or in these transistors, well, so far this is what I have to tell today. If you have any questions, please go ahead. Can you hear me?
Yes, thank you. Thank you very much for the talk. Let me see if I have questions in the YouTube, or you can also tip here, because there are some people that are... Sandro, did you see questions in YouTube?
Not at this moment. Of course, I have some questions, but they are more from the designer point of view.
Yeah.
So...
Yes,
so,
yes. I understand the density of information that I introduced today is pretty high. So it's
yeah, it is for sure.
It's not easy to digest the information in less than 1 hour.
Yes.
Yeah, but we have a very good, though small audience here, very specialized. So I think there will come some good questions. My on the designer side is about well, it's pretty much experimental measurements, right? Do you do some kind of modeling as well?
Yes, we are. We have 2 PhD students that are already working, and one of those is working together with Professor Vasileska, and he's already having some exchange of information with Professor Gilson Wirth. And the software that we are using is Monte Carlo. It's based on Monte Carlo solution of the Maxwell-Boltzmann equations, and so we are just fitting the variables in that model in order to make the electrothermal simulation at very low temperature. At this point in time, we are just able to run the electrothermal simulations at room temperature. So my student is already working on running those simulations down to cryogenic temperatures, but it's not an easy matter because there are plenty of numerical issues, and many times the software is not converging because of it's pretty complex in terms of numerical calculations. But yes, we have one PhD student working on that, on the modeling and simulation of electrothermal interaction at cryogenic temperatures.
Okay, so we have some comments here. Professor Sergio Bampi and Zuki are congratulating your presentation. And I have one question from Professor Marcelo Pavanello.
Oh, Marcelo.
He asks, are the soil transistors measured with all metal levels implemented?
The question is if we are measuring those devices with the metal levels?
With all the metal levels implemented in the design,
okay. That's information that I don't have, because but let me remember. Yes, I think so, because this test structure is in a test chip where there are many other test structures, even circuits. So I think we are using all the metal levels. All the metal levels are implemented in this particular chip.
Okay, great. Yeah. We have another question here from Professor Sergio Bampi. A question on the gate topology for the 10 micrometer width. Those are multi-finger FETs, I suppose. Do you see any problems with a non-uniform temperature across all the fingers?
Oh, okay, that's a good question. Well, there are at least, as far as I remember, at least 5 different FinFet test structures. There is one test structure with only one fin, and oh yes, yeah, okay. Let me see. Need to check my notes here. Yes, it depends on the number of fingers. So if you change the number of fingers, obviously the electrothermal interaction changes. So the electrothermal interaction or self-heating effect is also a function of the number of fingers. That is the answer for the question. We have seen that in some other experiments with devices with different numbers of fingers. Obviously,
okay. That's
if we are changing the number of fingers, we are changing the thermal properties. So the thermal properties are a function of the structure as well. So changing the number of fingers changes the thermal resistance, for instance, and also the thermal capacitance.
Okay, so how close do you think we are from getting to the quantum beat technology, really?
Oh, well, your question is how close are we in?
To get to the qubit, the quantum beat technology, really to see some, implementation, for instance.
As you know, I think last week there was a publication by IBM or Google. They showed the first, I think, 52 qubits quantum computer. And this is really experimental. So in order to have a computer which is capable of operating at the same level as the regular computers, I think is going to take at least some other, I don't know, maybe another decade, because there are still some issues, especially with the power consumption of the qubits, because each qubit is consuming power. If you put, let's say, 50 qubits, then you are increasing the joule power, and then the heating is going up. So you cannot keep the operating temperature down below, let's say, 1 Kelvin, which is the temperature operation for one of the qubits. So that is one of the big issues, how to control the power that is consumed by these qubits. That's the issue. That's a big issue. Again, it's an electrothermal problem.
Great. We have a follow-up question here. Well, you can go first, Gilson, please.
Yes, Edmundo, you did talk about the channel, the current in the channel, but you did not talk about the change in the source and drain parasitic resistance. Is because you wanted to focus on that, or because source and drain parasitic resistance really do not play no role in this study?
Okay, I quite not understand your point. So you mentioned that, okay, if you can repeat the question, please.
Yes, if source and drain parasitic resistance play a role or does not play any role in the study?
The source resistance, you mean?
Yes, source and drain resistance, yes.
Yeah, okay, yes, of course, but not only the electrical resistance, but also the thermal resistance, because there are not only electrons flowing through the source and the drain, as we measure as the drain or the channel current, but there is also heat flowing through the source and the drain, and the heat has to go through the vias and the metal, and then it goes up all the way up to the contacts. So indeed, the thermal resistance of the source and the drain is playing a key role in the electrothermal performance. So there are some other options in order to alleviate the self-heating effect at very low temperature. That means that we need to put a sort of pillars in the bulk, metal pillars through the bulk. Mm-hmm. And those metal pillars are a sort of heat exchangers. So they are helping the heat to go through the bulk and go away. But that means that we need to change or redesign the technology for cryogenic operation. And that is also a comment that I want to mention here. If we want to, so we cannot use, or it's going to be very hard to use commercial CMOS technologies that operate at room temperature for cryogenic temperatures, because we need to make some adaptations to the technology in order to be more electrothermal friendly for the cryogenic operations, such as putting some heat exchanger through the bulk, for instance, using these metal pillars through the bulk. Mm-hmm. So yes, indeed, we need to have a cryogenic CMOS technology designed specifically for this operation. If we need to, yeah,
making thinning the silicon, using thinner silicon, also making a back contact, something like that.
Yes, using a thinner silicon and using also back contacts might be a solution, because you are helping the heat to go away from the active region of the transistor. But then you have the problem. You have the problem there because you need to do something with that heat. So that is heat that is being generated and then has to go away. Yes. And we need to find a heat channel in order to avoid the critical region to heat up.
Thank you. Thank you so much. Thank you for your great talk. Thank you so much.
Thank you. Well, we have some other question here from Sergio Bumpy, but it's basically on the same talking about the source and then drain connections. We also have a comment from Poncho Cabrera is thanking you for the presentation.
I know.
And we don't have additional questions here.
Okay.
So Professor Gilson wants to close the session. It was really a pleasure. And well, I have to dig into the presentation later so that I can understand it better, right? But okay. It was really nice, very informative.
Yeah, thank you for inviting me to talk. And then we are working on a couple of papers. Perhaps when the papers are ready, they will be published, and then there you will find some more details on this work. So thank you, everyone, for the questions and for inviting me for this distinguished lecture program.
Thank you so much for accepting the invitation. It's really a lot of information, yes, but thank you really much. We'll take some time to digest it, to understand it.
So yes, we can get in contact later if you want, yes. If you have specific questions or if you want to start some collaboration as well. So I'm open for that as well.
Thank you, sir. Thank you very much, and thank you so much for the excellent talk. Yeah.
Okay, thank you. Then I think we are closing the session.
Yes, we are closing the session now. So thank you very much once again. It was a pleasure to have you here.
Okay, bye then.
Bye.